Tonight, we're going to look at the edge of the solar system and at the strange fact that nobody can agree on where it is. In August of 2012, a spacecraft called Voyager 1 crossed a boundary about 121 times farther from the Sun than the Earth is. The world was told it had left the solar system. It was the kind of sentence that gets read aloud on the evening news and then filed away as settled, and for most people, it has stayed settled ever since. Sunlight reaches that boundary in about 17 hours. Sunlight needs as much as a year and a half to clear the outermost edge of what the Sun still holds. Voyager had crossed roughly 1,000th of the way out, and we called it leaving. That gap is not a rounding error. It is the difference between stepping off a porch and crossing an ocean, and the consequence of it reaches into every object our species has ever launched. The probes carrying our recorded voices outward will be cold and silent long before any of them arrives at the real edge. Their power fails sometime in the 2030s. The instrument that reported crossing the boundary in 2012 will have been dead for roughly 270 years by the time it reaches the inner limit of the last region the Sun governs, and by NASA's own estimate, it will need another 30,000 years to pass beyond the outer one. Nothing we have built will be awake for the crossing. Nothing we have built was ever going to be. So where does the solar system actually end? By the end of tonight, you're going to understand exactly which boundaries working scientists use to answer that question, why those answers disagree with each other by a factor of roughly 4,000, and which one of them has the strongest claim to the name. Before we get started, if you love exploring the outer reaches of our own solar system as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The trouble starts with the word itself. An edge, in ordinary life, is a thing you can put a hand on, a coastline, a property line, the last stair. Every edge you have ever encountered had the decency to be somewhere and to stay there while you walk toward it. The solar system offers nothing of the kind. It offers a series of thresholds, each one real, each one measurable, each one defensible as the answer, and each one at a wildly different distance from the last. Choosing among them is not a matter of better instruments. It is a matter of deciding what the word solar system is supposed to mean. The question sounds like it should have a single number attached to it, the way the height of a mountain does. It does not. Ask an astronomer where the solar system ends, and you will get a clarifying question in return, because there are at least 4 honest answers, and they are not close to one another. The first answer is the planets. That boundary sits at about 30 times the Earth-Sun distance, out at Neptune. The second is the Kuiper Belt, the field of icy bodies beyond Neptune, which thins out around 50. The third is the heliopause, the place where the Sun's wind finally stops pushing and the gas between the stars takes over. That is where Voyager crossed, at about 121. The fourth is the Oort Cloud and the gravitational domain that contains it, which may reach 100,000 times the Earth-Sun distance, and by some estimates twice that. 30, 50, 121, 100,000. The last number is not a little larger than the first. It is more than 3,000 times larger. If the planetary boundary were the width of a dinner plate on the table in front of you, the gravitational boundary would be a circle just over half a mile across, centered on that plate, with the whole neighborhood inside it. Both circles are drawn around the same star. Both are correct. They are answering different questions. This is the first thing worth carrying through the rest of the night. The disagreement is not a sign that the science is unfinished. Every one of those boundaries has been measured or bounded by good models. The disagreement is a sign that where does it end was never a purely physical question. It smuggles in a definition, and the definition does the heavy lifting. Notice what each of the four is tracking. The first marks where the large bodies stop. The second marks where even the small ones thin out. The third marks where a thin, fast wind of charged particles loses its contest with the gas drifting between the stars. The fourth marks where the sun's pull on a distant object finally becomes weaker than the pull of the rest of the galaxy. Those are four different properties of the same star, and there is no reason they should end in the same place. A lighthouse has a structure, a pool of light, a range at which its horn can be heard, and a stretch of coast whose shipping it governs. All four are real. All four have different radii. Nobody finds this confusing about lighthouses. We will walk out through all of them, in order, starting with the one you were taught first, and the one that is least defensible when you look at it closely. Before we go anywhere, we need a way to talk about these distances that does not turn immediately into a wall of digits. Astronomers use the astronomical unit, which is simply the average distance from the Earth to the Sun, about 93 million miles. It is a convenient ruler for the inner solar system and an increasingly useless one further out, because the numbers grow faster than intuition can follow. 30 of them is Neptune. 100,000 of them is a figure the mind refuses to hold. So tonight we will use a second ruler alongside it, and it is the one the sun itself provides. How long its light takes to arrive. Sunlight reaches the Earth in about 8 minutes. It reaches Jupiter in roughly 3/4 of an hour. It reaches Neptune's orbit in about 4.5 hours. So a photon that leaves the sun as you sit down to a late dinner is passing Neptune before the house is fully quiet. That same photon reaches the heliopause, the boundary Voyager crossed, in about 17 hours, not days, hours. The entire heliosphere, the whole bubble of the sun's wind containing every planet, every moon, every asteroid, both Voyagers and every human being who has ever lived, is less than a day wide at the speed of light. Then the ruler breaks. To reach the inner edge of the Oort Cloud, that photon needs somewhere between 10 and 28 days more. To pass the Oort Cloud's outer edge, it may need as much as a year and a half. 17 hours, and then a year and a half. Hold on to that pair. We are going to come back to it 3 times tonight, from 3 different directions, and each time it will mean something slightly different than it did before. It is worth sitting with why that jump is so violent. Everything from the sun's surface out to the heliopause, the entire mapped, photographed, visited portion of the solar system, fits inside less than 1 day of light travel. Every mission ever flown, every image ever returned, every rock ever sampled occupies a region a photon crosses between one evening and the next. And then, to finish the journey outward, that same photon needs to keep going for another 18 months. There is no comparable step anywhere else in our experience of scale. It is as though a house had ordinary rooms, and then, past the back door, a garden the size of a continent. The first boundary is the one every schoolroom teaches, and it is the easiest to describe. The solar system ends where the planets end. Neptune orbits at about 30 astronomical units. Beyond it, in the classical picture, there is nothing worth naming. That is the version printed on the poster. 9 bodies, later 8, arranged in tidy concentric rings, each one comfortably visible, the whole system fitting neatly on a single sheet of paper. That poster is not a simplification. It is a distortion, and the distortion is almost entirely one of scale. Consider what an honest diagram would require. If the Earth's orbit were drawn as a circle 1 inch across, Neptune's orbit would be 30 inches across. A large sheet of paper, but manageable. On that same scale, the heliopause would sit about 10 feet from the center. The inner edge of the Oort Cloud would be between 160 and 400 feet away, past the end of the street. And the outer edge would be more than a mile and a half off, several neighborhoods over, still centered on that 1-inch circle. No printer makes that page. So the page lies, and it lies in a very specific direction. It makes the solar system look like a place with contents and a border, rather than what it actually is, which is a single bright object surrounded by an enormous volume of nearly empty space that happens to contain a few specks. The planetary boundary survives in our heads, not because it is defensible, but because it is drawable. Everything past Neptune got left off the poster, and what gets left off the poster stops feeling real. There is a second distortion in that poster, and it is subtler. The planets are drawn as though they hold the system together, the way beams hold a roof. They do not. Add every planet, every moon, every asteroid and comet and grain of dust together, and the total comes to about 0.1% of the mass of the solar system. The sun is the other 99.9. Everything else, including this world and everyone on it, is residue left over after a star finished forming. Which means the honest picture is not a system of worlds with a star at the middle. It is a star, alone, with some debris in orbit and a domain that extends outward for a light year and a half in every direction. The planets are a detail near the center. They are simply the detail we happen to live in. The second boundary is the Kuiper Belt, and it is the point where the tidy picture starts coming apart. Beyond Neptune, at about 30 astronomical units, a broad field of icy bodies begins. It extends out to roughly 50. Astronomers have cataloged more than 2,000 objects out there so far, and the models suggest hundreds of thousands of bodies larger than 60 miles across, along with an uncountable population of smaller ones. Pluto is one of them. So is every world you have heard about with an unfamiliar name and an odd orbit. 2 details matter for tonight. The first is that the Kuiper Belt is not a ring. The word belt invites you to picture something flat and narrow, a lane of traffic circling the sun. It is better described as a puffed up disk or a donut, thick, unevenly populated, with objects tilted well out of the plane the planets share. Even at this modest distance, the solar system has stopped being a diagram and started being a volume. The second detail is the mass. Every icy body in the Kuiper Belt, added together, comes to no more than about a tenth of the Earth. An entire region of the solar system, spanning 20 astronomical units of depth and containing hundreds of thousands of worlds, weighs less than the ground under one continent. And this is the part that rarely gets said out loud. This is what the outer solar system is mostly made of. Not planets, not moons, scattered debris spread so thin that if you were standing on one Kuiper Belt object, the nearest one would almost certainly be invisible, millions of miles off, a point of reflected sunlight indistinguishable from a faint star. The belt is a statistical fact rather than a scene. You could fly through it for years and never see anything at all. The New Horizons spacecraft demonstrated this the hard way. After passing Pluto in 2015, it spent years searching for a second target it could reach with the fuel it had left, and the search was difficult precisely because the region is so empty. It eventually flew past a small double-lobed body about 22 miles long, a billion miles beyond Pluto, in the first hours of 2019. That was the entire haul. One additional object in a field of hundreds of thousands. From the sun's perspective, the Kuiper Belt is dense. From inside it, it is the emptiest place any of our machines have ever been. And it is not remotely the edge. There is a story from the last 20 years that belongs here because it is this entire episode in miniature. In 2006, Pluto stopped being a planet. Nothing happened to Pluto. It did not shrink or move or lose a moon. Its orbit continued exactly as before, carrying it between about 30 and 50 astronomical units from the sun on a 248-year circuit it has been running since long before anyone was watching. Every physical fact about the object was unchanged on the day after the vote. What changed was a definition. Astronomers had begun finding other bodies out in the Kuiper Belt of comparable size, and it became clear that either the solar system had a great many planets or the word needed tightening. They tightened the word. Pluto fell outside the new boundary, and a generation of textbooks was quietly reprinted. People were genuinely upset about this, and the upset is instructive. It felt like a loss, as though something had been taken out of the sky. But the sky was untouched. What had been revised was a category, a line drawn by people through a population of objects that had never been consulted about which side of it they were on. Keep that in mind as we go outward tonight, because we're about to do exactly the same thing on a much larger scale. Every boundary still ahead of us. The wind's edge, the ice's edge, the reach of gravity, is a line of the same kind. Each one is drawn through a smooth continuum, at a place chosen because it is measurable and useful, not because the solar system does anything abrupt there. Pluto is the small, well-lit version of the problem. The edge of the solar system is the large, dark one. The difference is only that the second one is harder to argue about, because almost nobody has a childhood attachment to the heliopause. There is no poster of it on any classroom wall. When astronomers revise where they think the sun's gravitational reach gives out, no textbooks get reprinted and no one writes a letter of complaint. The boundary moves quietly in journals, and the public keeps the version it was given. which is how a spacecraft crossing one particular threshold in 2012 became, in the public record, the moment humanity left the solar system, and stayed that way for 14 years. Before we leave the ice behind and move on to the wind, there is a complication in the Kuiper Belt worth naming, because it is the first hint of the pattern that governs everything further out. The belt does not stop at 50 astronomical units. It thins there. The population drops off sharply enough that 50 is a reasonable place to say the main region ends. But beyond it lies something called the scattered disk, and the scattered disk reaches to nearly 1,000 astronomical units, with individual bodies on orbits that carry them farther still. These are objects thrown outward, most likely by close encounters with Neptune early in the solar system's history, onto long, tilted, elongated paths. They spend most of their time far out in the cold and dark, and only briefly swing back toward the region where we can see them. Their orbits are not stable circles. They are the tracks of things that were flung. So the second boundary, examined closely, dissolves in the same way the first one did. There is no wall at 50. There is a dense region, then a less dense region, then a very sparse region, and the numbers we quote are chosen where the fall-off is steepest, because that is the most useful place to draw a line. Not because anything changes there. You will see this exact structure at every remaining boundary tonight. The wind does not stop. It slows, then stalls, then loses. Gravity does not switch off. It weakens until something else is stronger. In every case, the honest description is a gradient. And in every case, we replace the gradient with a number, because a number can be printed and a gradient cannot. The solar system is not a country with a border. It is a city with suburbs, and then outer suburbs, and then a long stretch of road where the streetlights get farther apart. And at some point, you are simply in the countryside, and nobody can tell you which streetlight was the last one. This is worth accepting early, because the alternative is to spend the rest of the night waiting for a boundary that satisfies. There is not one. What there is instead is a sequence of thresholds, each of which tells you something true about the sun, and each of which is somebody's reasonable answer to the question you came here with. The third boundary is made of something you cannot see, and it is the first one that behaves like an actual physical structure rather than a population count. The sun is not only emitting light, it is leaking. A steady stream of charged particles, mostly protons and electrons, escapes its outer atmosphere and flows outward in every direction at speeds typically between about 700,000 and 1.5 million miles per hour. This is the solar wind, and it never stops. It has been blowing for 4.5 billion years, and it will keep blowing until the sun itself changes. That wind inflates a bubble. It pushes outward against the thin gas and dust that drifts between the stars, and it keeps pushing until the two pressures balance. The volume inside that balance point is called the heliosphere, and everything familiar lives inside it. The sun, the planets, the Kuiper Belt, the scattered disk, both Voyager spacecraft, and the entire history of our species. The bubble is not a sphere, despite the name. The sun is moving through the galaxy, and the interstellar gas flows past it the way water flows past a moving boat. So the heliosphere has a blunt, compressed nose on the leading side and a long, drawn-out tail behind, more like a windsock than a balloon. Recent modeling has suggested shapes stranger still. One supercomputer study proposed a structure with spiral arms of its own, though the outer form remains genuinely uncertain because we have only ever measured it from 2 points, and both of those were headed roughly the same way. What matters for tonight is the nose, because that is where our 2 probes went, and that is where the boundary was crossed. There is one more property of this bubble worth holding on to, and it is the reason the heliosphere is more than an item of trivia. It is a shield. The galaxy is full of cosmic rays, atomic nuclei accelerated to nearly the speed of light by supernovae, arriving from every direction continuously. The solar wind and the magnetic field it carries deflect a substantial fraction of them before they reach the inner solar system. So the bubble is not merely where the sun's influence happens to reach. It is a region of shelter maintained by a star inside a galaxy that is otherwise sleeting with high-energy particles. Every living thing that has ever existed has existed inside it. The wind, in other words, has a job. It is not just exhaust. It is the outer wall of the only room our species has ever been in. Crossing out of the bubble happens in stages, and the first stage has a name: the termination shock. Out at the edge of the heliosphere, the solar wind runs into the accumulated pressure of the interstellar gas ahead of it and abruptly slows from supersonic to subsonic. The particles pile up, heat, and change direction. It is the same physics as the standing ripple where a fast stream of water from a tap spreads across a flat sink and then suddenly thickens into a ring. The flow does not stop, but it stops being able to outrun its own pressure waves. Voyager 1 crossed the termination shock in December of 2004 at 94 astronomical units from the Sun. Voyager 2 crossed it in August of 2007 at 84. Read those 2 numbers again, because the gap between them is the most important thing in this segment. The same boundary, measured by 2 nearly identical instruments, was found 10 astronomical units apart, a discrepancy roughly a third the size of Neptune's entire orbit. That is not a measurement error. Both crossings were unambiguous and well recorded. The boundary was simply in a different place. Part of the difference is direction. The 2 spacecraft left the solar system on different headings, and the bubble is not symmetric. Part of it is time. The sun's activity rises and falls on a cycle of roughly 11 years, and when the sun is more active, the wind pushes harder, and the bubble inflates. When it quiets, the bubble settles inward. Voyager 2 arrived at a different point in that cycle than its twin. The edge of the solar system, on this definition, breathes. It is not a place a surveyor could stake out. It is a pressure balance that shifts with the weather of a star. Voyager 1 had an additional difficulty, and it is a small human detail worth keeping. Its plasma instrument, the one designed to measure exactly this, had failed years earlier. The spacecraft passed through the most anticipated boundary of its mission partly blind, and the crossing had to be reconstructed from the magnetometer, the particle detectors, and the cosmic ray telescope. Voyager 2's plasma instrument still worked, which is why its crossings are the better documented pair, even though it arrived second. Consider what that means about the state of the evidence. Everything we know by direct measurement about the outer boundary of the sun's wind comes from two spacecraft designed in the early 1970s, launched 16 days apart in 1977, traveling in roughly the same direction, one of them missing a key instrument. That is the entire data set. We have mapped the edge of the solar system the way a person might map a lake, by wading in at two neighboring spots on the same shore. The second stage is the heliopause, and this is the line that made the headlines. Voyager 1 crossed it on the 25th of August, 2012, at about 121 astronomical units. Voyager 2 followed on the 5th of November 2018 at about 119. It is worth being precise about what happened because the precision is where the story lives. Nothing was visible. There was no wall, no membrane, no flash on any camera. What the instruments recorded was a change in the surrounding plasma. The thin, hot, fast-moving gas of the solar wind gave way to the denser, colder, slower gas of the interstellar medium. The density of charged particles jumped by a factor of roughly 40. The count of cosmic rays arriving from the wider galaxy rose and stayed risen. In other words, Voyager crossed the outer surface of a bubble of wind. On one side, the particles around it came from the sun. On the other side, they came from everywhere else. That is a genuine, sharply defined boundary, and detecting it was a real achievement of instrumentation and patience. It deserved the coverage it received. What it was not is the edge of the sun's domain. The sun's gravity at 121 astronomical units is still, by an enormous margin, the dominant influence. Objects out there orbit the sun. Objects 1,000 times farther out still orbit the sun. Voyager itself was on an escape trajectory, but it had bought that trajectory with gravitational assists from Jupiter and Saturn decades earlier, not by reaching some line beyond which the sun no longer pulls. The spacecraft left the sun's wind. It did not leave the sun. NASA was careful about this at the time, and the care did not survive contact with the public. The agency's own language described Voyager as having entered interstellar space, which is accurate. The material around it is now interstellar material, but entered interstellar space and left the solar system are not the same claim, and the second one traveled much better than the first. You can see why. One of them is a clean sentence with an ending in it. The other requires a paragraph about wind versus gravity, about the fact that there are several boundaries, and this was one of the closer ones. Headlines do not have room for that paragraph, and by the time anyone writes it, the simpler version has already been filed as known. So this is the correction, stated plainly, 14 years late. In 2012, a spacecraft left the region dominated by the sun's wind. It remains tonight deep inside the region dominated by the sun's gravity. It will remain there for the rest of its existence as a recognizable object, and so will everything else we have ever launched. Set the spacecraft aside for a moment and look at the distance itself. The heliopause sits at roughly 120 astronomical units. In the ruler we chose earlier, That is about 17 hours of sunlight. A photon that left the sun's surface at sunrise is crossing that boundary, the one the news called the edge of the solar system, before sunrise the following day. Everything you have ever heard of is inside that 17 hours. Every mission, crewed and uncrewed, every planet and every moon, the Kuiper Belt in its entirety, the scattered disk, every image ever returned by any instrument our species has built. The whole of it fits inside a single day of light travel, and most of it fits inside the first 5 hours. Now put the second number next to it. To pass the outer edge of the Oort Cloud, the outermost region that still belongs to the sun in any meaningful sense, that same photon may need as much as a year and a half. 17 hours and then 18 months. Say it as a ratio and the shape of the night becomes clear. The mapped solar system, the one in every book and every mission log, is about 1,000th of the sun's actual domain. Not a 10th, not 100th, 1,000th, and possibly less, since the outer figure is a floor as often as a ceiling. There is a particular quality to that kind of number. It is not the ordinary largeness of astronomy, where things are big and you nod and move on. It is a statement that the object you thought you were looking at was a detail in the corner of a much larger object, and that nobody mentioned this because the larger object is invisible and always has been. The wind's edge is real. It is simply not the edge of the thing. It is closer to the last well-lit room in a house whose grounds run for miles past the windows. There is a further consequence hidden in that ratio. Discussions of interstellar travel usually begin at the heliopause, as though getting there were the hard part and the rest a longer version of the same problem. The arithmetic says otherwise. Reaching the heliopause took 35 years with the technology of 1977. Reaching the far side of the sun's own gravitational domain on the same trajectory takes something on the order of 30,000. Leaving the solar system is not a journey with a finish line a few decades out. It is a journey whose first tenth of 1% has taken us half a century and is, so far, the only part any human-built object has completed. It is worth taking a moment to imagine actually being there, because the imagining corrects something the phrase edge of the solar system does to the mind. You are at 121 astronomical units. Turn and face inward toward home. The sun is still the brightest object in your sky by an overwhelming margin. It is not a disk anymore. At this distance, it has shrunk to a point no wider than any other star, but it is a point roughly as bright as the full moon looks from Earth. It still casts shadows. You could read by it, slowly, if you had something to read. It is unmistakably the local star, and everything around you is unmistakably in orbit around it. Now look outward. Nothing. No line, no shimmer, no marker of any kind. The boundary you have supposedly crossed is a change in the density and temperature of a gas so thin that calling it a gas is generous, a few dozen charged particles per cubic inch, where a breath of air at sea level holds a number with 20 digits in it. You would pass through the most famous boundary in modern space exploration without any sensation whatsoever, and without any instrument on your person registering the event. And this is the honest thing about all of it. None of these edges are experiences. They are readings. The heliopause is a place where a particular counter changes its number. And the only reason we know it exists at all is that we sent something out with the right counter aboard and waited 35 years. If you were traveling out there without instruments, you would have no way of knowing where you were, or which of the 4 boundaries you had already passed, or how many were still ahead. You would only know that the sun was getting fainter, extremely slowly, and that it would keep doing that for a very long time. Space offers no discontinuities of the kind our senses were built for. What it offers are gradients spread across distances so large that the change is undetectable at any point along the way and only becomes apparent when you compare 2 measurements taken decades apart. The heliopause is the sharpest boundary in the outer solar system, and even it took a spacecraft several months to fully cross. We keep going out there looking for a shoreline and finding weather instead. Between the wind's edge and the beginning of the next region, there is a gap, and the gap deserves its own name because almost nothing is ever said about it. Voyager crossed the heliopause at about 120 AU. The inner edge of the Oort Cloud is estimated to begin somewhere between 2,000 and 5,000. That leaves a stretch of roughly 2,000 astronomical units, 16 times the entire distance from the Sun to where Voyager crossed, in which there is essentially nothing at all. No wind from the Sun to speak of. No population of icy bodies dense enough to name. A handful of scattered disk objects on their long elliptical falls, and otherwise a volume of space that our science has no reason to describe, because there is nothing in it to describe. This is the part of the solar system nobody draws. It has no features, no discoveries attached to it, no missions planned. It is simply the distance you have to cross between the last thing and the next thing, and it is more than an order of magnitude wider than everything covered so far tonight. Our machines will spend centuries there. Voyager 1 entered that stretch in 2012 and will still be crossing it in the year 2300, and in 2400, and in 2500, dark and cold and tumbling. Its plutonium long since decayed past the point of powering anything, still moving at the same 17 kilometers per second it had when it left, because there is nothing out there to slow it down. That is the real texture of the outer solar system, not a frontier. A long, unlit corridor between 2 thin populations of ice with a dead spacecraft in it. The emptiness has one practical consequence. Because there is nothing out there to interact with, nothing out there changes. An object crossing that corridor is not weathered, not eroded, not slowed, not heated. The gold-plated record bolted to Voyager's side, with its recorded greetings and its diagram of where we live, will be in the same condition in the year 5000 as it is tonight. Not preserved by anyone, simply undisturbed because there is nothing in the volume of space to disturb it. The outer solar system is not hostile in the way a desert or an ocean is hostile. It is something rarer and harder to picture. It is inert. It does not act on what passes through it at all. And it goes on like that, past the point where any human time scale remains useful, until the ice begins. The 4th boundary is the strangest thing in this episode, because it is the largest structure associated with our sun, and no one has ever directly observed it. It is called the Oort Cloud, and its existence was inferred rather than discovered. In 1950, the Dutch astronomer Jan Oort was studying the orbits of long-period comets, the ones that take more than 200 years to complete a circuit, sometimes far more, and he noticed something in the numbers that demanded an explanation. These comets arrive from enormous distances. Their orbits trace back to points tens of thousands of astronomical units out, and critically, they did not arrive from any particular direction. They came from above the plane of the planets, below it, and at every angle in between, with no pattern favoring the flat disk where everything else in the solar system lives. Oort's conclusion was that there must be a vast reservoir of icy bodies out there, arranged not as a belt but as a shell, a roughly spherical swarm surrounding the sun and everything else at distances so great that the bodies within it are only loosely held. Occasionally, something disturbs one. It falls inward, takes thousands or millions of years to make the journey, rounds the sun, grows a tail, is observed by someone on Earth for a few weeks, and departs. Every long-period comet in recorded history has been a single visitor from that population. We have never seen the population itself. We have only ever seen the ones that fell. That is the evidentiary situation, and it is worth stating without decoration. The largest region of the solar system is known to us entirely through the small number of its members that have left it. The idea was not entirely without precedent. The Estonian astronomer Ernst Öpik had proposed something similar in 1932, working from a different line of reasoning, which is why the region is occasionally called the Oort Cloud in the literature. But it was Oort's 1950 paper, built on the statistics of comet orbits, that made the case convincingly enough to become the standard picture. And it has survived 76 years of subsequent scrutiny without being replaced. What it has not acquired in those 76 years is a photograph. Not one image of one Oort cloud object in its home orbit exists. The bodies are small, dark, extraordinarily far away, and receive so little sunlight that reflecting enough of it to register on any telescope we have built is out of the question. We know the cloud is there the way you know a room is occupied, because things keep coming out of the doorway. Everything in the next several segments rests on that inference. It is a strong inference, supported by decades of orbital data. It is still an inference. The Oort cloud's dimensions are usually given as ranges, and the ranges are wide enough that they look at first like an admission of failure. They are not. They are the honest shape of the knowledge. The inner edge is thought to lie somewhere between 2,000 and 5,000 astronomical units from the sun. The outer edge is placed somewhere between 10,000 and 100,000. Look at that second pair. The outer boundary is uncertain by a factor of 10. The high estimate is not a refinement of the low one. It is 10 times farther out, describing a volume 1,000 times larger. And both figures appear, without embarrassment, in the same reference material, because the truth is that the cloud has no sharp outer surface, and the population simply thins until it stops being meaningfully bound. In light travel terms, the inner edge is 10 to 28 days out. The outer edge, at the high estimate, is about a year and a half, roughly 1 6/10 light years. NASA describes the region as extending 1/4 to halfway from the sun to the next star. Read that phrase slowly, because it contains the whole scale of the thing. Not 1% of the way to the next star, not 5%, a quarter of the way, and possibly half. The sun's icy debris field extends a substantial fraction of the distance to Proxima Centauri, which sits 4.25 light years away. The nearest star is not across an empty gulf from us. It is across a gulf that our own solar system has already filled a good part of, with objects that are still, technically, ours. The internal structure of the cloud is usually described in two parts. The inner region, sometimes called the Hills cloud, after the astronomer who proposed it, is thought to be denser, more populous, and somewhat flattened, still carrying a trace of the disk the objects came from. The outer region is the true shell, thinner, spherical, and held so weakly that its members can be nudged onto new paths by influences from outside the solar system entirely. That weakness is the defining property of the outer cloud, and it will matter twice more tonight. An object 50,000 astronomical units from the sun is bound to it, but barely. It orbits at a walking pace, a few dozen yards per second, slower than a car on a highway, and takes millions of years to complete one circuit. It would take very little to take it away. Out there, the sun's grip is real, and it is the grip of a hand that has almost let go. The Kuiper Belt is flat because the solar system formed flat. Everything close in, the planets, their moons, the asteroids, the belt, condensed out of a spinning disk of gas and dust, and a spinning disk leaves its geometry stamped on everything it makes. That is why the planets all orbit in nearly the same plane, in the same direction, like grooves on a record. The Oort Cloud does not share that geometry, and the evidence for the difference is simple enough to state in a sentence. Long-period comets arrive from everywhere. If the outer reservoir were a flat extension of the disk, the comets falling in from it would arrive along the plane of the planets, the way Kuiper Belt objects do. Instead, they come down from high above the plane, up from far below it, and in from every intermediate angle, with their orbital tilts distributed roughly at random. Some of them travel around the sun in the opposite direction from the planets, which nothing born in the original disk would do. That randomness is the fingerprint of a shell. The only way to produce comets arriving with no preferred direction is to have a source population arranged with no preferred direction. A swarm surrounding the sun on all sides, not a ring around its waist. How a flat system produced a spherical outer shell is itself worth knowing. The Oort cloud bodies almost certainly did form in the disk, close to the giant planets, and were flung outward by encounters with them. Jupiter and Saturn are extraordinarily efficient at throwing small things very far. Once out at those distances, the objects came under the influence of passing stars and the gravity of the galaxy itself, which stirred their orbits over billions of years until the original flatness was scrambled away. So the shape of the cloud is a record of its own history. Born in a disk, thrown out by planets, and then stirred for 4.5 billion years into a sphere. It also means the material out there is old in a particular way. These are bodies that formed early, were evicted before they could be incorporated into anything larger, and have spent the entire history of the solar system in deep cold, unmodified. When a long-period comet falls in and begins to shed gas near the sun, What it releases is chemistry that has been in storage since before the Earth had a surface. Estimates of the Oort Cloud's population run to hundreds of billions of icy bodies, and by some accounts, trillions. Set that against the observational record. We have cataloged a few thousand comets that came from there across the entire history of astronomy. We have never imagined a single Oort cloud object at its home distance. We have never measured the mass of the cloud directly, never determined its composition except by inference from the comets that fell, never established where its outer surface is to better than a factor of 10. And here's the thing that follows from that, said plainly. By volume, the overwhelming majority of the solar system is a region we have characterized entirely by indirect means, containing a population we have never counted, bounded by a surface we cannot locate. That is not a criticism of anyone. It is a consequence of physics. An object out at 50,000 astronomical units receives sunlight 2.5 billion times weaker than the Earth does. A body of that kind, a few miles across and dark to begin with, reflects a quantity of light no telescope now existing or seriously planned could detect at that range. We are not going to see the Oort cloud. Not with better instruments, not this century, probably not ever from where we are standing. The only realistic path to a direct observation is to send something out into it, and the timetable for that is the subject of 2 segments from now, and it is not encouraging. Meanwhile, the cloud sits there, containing more individual worlds than every star in the Milky Way, entirely dark, entirely silent, surrounding everything we have ever known in every direction. There is a particular kind of vertigo available in that fact. Look up on any clear night, and what you see is the interior of a lit room. The sun, the planets, a handful of nearby stars, the band of the galaxy behind them. What you do not see and cannot see is the shell of ice standing between you and all of it, in every direction you could possibly look, at a distance so great that the sunlight now reaching its outer bodies departed the sun 1.5 years ago. It is not a barrier. The objects in it are separated by tens of millions of miles, and a spacecraft could pass through without ever coming near one. But it is there, and it is ours, and it is the largest thing our star has. Everything you can see is inside it. Every image ever taken from within the solar system was taken from a point deep inside it, and none of them show it. There is a single object that gives us something close to a direct look at that region, and it was found in 2003. Its name is Sedna. It is a small reddish world in the outer solar system, and its orbit is the reason it matters. At its closest approach to the sun, Sedna comes in to about 76 astronomical units, well outside the Kuiper Belt, well outside Neptune's reach. At its farthest, it goes out to roughly 937. A single orbit takes it about 11,400 years. That orbit is a problem for the tidy account of how the solar system is arranged. Sedna never comes close enough to Neptune to have been placed on that path by Neptune, the usual explanation for extreme outer orbits. It is what astronomers call a detached object, detached from the gravitational influence of the planets. Something else put it there, and the leading candidates are an encounter with a passing star early in the sun's history, the cluster of stars the sun was born among, or a body still undetected in the outer system. Some astronomers count Sedna as a member of the inner Oort Cloud. Whether that classification holds depends on exactly where you put the cloud's inner edge, which returns us, once again, to the theme of the night. The object is fixed and well measured, and its category is a matter of where somebody draws a line. Here is the detail worth keeping. Sedna last passed its closest point to the sun a few centuries ago, and before that, the previous time it came in, the Earth was in the last stages of its most recent ice age. Sedna has completed roughly one orbit in the entire span of human civilization. When it next returns to where it is now, no arrangement of human affairs that exists tonight will have any meaning at all. And Sedna, remember, is the near one. Its farthest point, out at 937 astronomical units, does not reach even the low estimate for the inner edge of the Oort cloud. The most distant object whose full orbit we have measured spends its loneliest centuries in the empty corridor, still short of where the cloud is thought to begin. A handful of similar bodies have been found since, on comparable detached orbits. They are called sednoids, and there are fewer than a dozen confirmed, every one found near its closest approach, the one brief phase of an orbit lasting many thousands of years when the object happens to be near enough to catch the light. We are surveying that population, the way you might survey a city by standing at a single window and noting whoever walks past. Return to the ruler, because the cloud is where it finally comes apart. Sunlight crosses the inner solar system in hours. It reaches the heliopause, the boundary that made the headlines, in about 17 of them. It then requires another 10 to 28 days to arrive at the inner edge of the Oort cloud, and to pass beyond the outer edge, it may need as much as a year and a half. Follow what that does to the shape of the thing. If sunlight leaving the sun tonight were a traveler, it would clear the entire mapped solar system before tomorrow evening. It would still be crossing the empty corridor at the end of the month. It would reach the first ice of the outer cloud sometime around the middle of the next month, and it would still be inside the sun's domain at this hour next year, and the year after that, halfway through. The same light. The same journey. 17 hours and then 18 months. There is one more consequence in that number, and it is the strangest of the night. Light is the fastest thing that exists, and the solar system is wide enough that even light takes over a year to leave it. Any signal, any message, any warning sent from the sun outward at the maximum speed the universe permits is still inside the sun's own domain a full year after it departs. Whatever else the solar system is, it is not small. We have simply spent all of our history in the brightly lit thousands of it and drawn our maps from there. It is worth noticing what that does to the familiar comparison between the solar system and the galaxy. The usual framing treats them as different orders of thing. The solar system as a place, the galaxy as the vast arena the places sit in. The light travel figures do not support that framing as cleanly as it is usually offered. Our star's domain is a substantial fraction of the way to its nearest neighbor. Line up the sun's outer cloud and Proxima's, if Proxima has one, and there may not be much genuinely empty space left between them. The stars are not scattered points with nothing in between. They are more like a crowd standing at arm's length, each one surrounded by a cloud of its own debris, the outer edges nearly touching. Which raises a question we will come back to at the end of the night: whether the sun's outermost ice and the ice belonging to the next star over are in any meaningful sense separate at all. Put a spacecraft against those distances, and the arithmetic becomes difficult to read without flinching. NASA's own published estimate is that Voyager 1 will not enter the Oort Cloud for about 300 years, and will not exit its outer edge for perhaps 30,000. That first figure rewards a moment of arithmetic because it quietly contains the whole argument of this episode. Voyager covers about 3.5 astronomical units a year, and it is currently a little past 170. 300 years at that rate brings it to roughly 1,250, which is not 2,000. It is not 5,000 either. What the 300-year figure actually encodes is a particular choice about where the Oort cloud starts, the near end of the range, the region sometimes called the Hills cloud, rather than the conservative 2,000 unit figure quoted more often. Take the far end instead, and the same spacecraft at the same speed needs something closer to 500 years. That is not a contradiction, and it is not an error by anyone. It is the same thing happening for the fourth time tonight. The number depends on the boundary, and the boundary is a choice. Even a travel time, the most concrete sounding quantity in astronomy, a spacecraft and a distance and a speed, turns out to be a statement about a definition. What is not in dispute is the order of magnitude. Centuries to arrive, tens of millennia to pass through. Those hold under every reasonable definition, and they are the ones that matter. Now set them against the machine. The Voyagers are powered by the decay of plutonium, and that decay is relentless and well understood. Instruments have been switched off one by one for years to conserve what remains. Sometime in the 2030s, the last of them will go quiet, and after that, the spacecraft will not be a mission. It will be an object. So the sequence is this. The probe goes silent in the 2030s. It reaches the inner edge of the Oort cloud around the year 2300, dark. It is still crossing the cloud in the year 10,000, and in the year 20,000, dark. It leaves the sun's outermost region sometime around the year 32,000, dark, cold, and unattended, having spent more than 99.9% of its journey as a dead thing. There will be no report from the edge. Not from this spacecraft, not from its twin, not from anything currently built or seriously proposed. The boundary that actually defines our solar system will be crossed by the only objects we have ever sent, tens of thousands of years after the last person who worked on them has been forgotten. And nobody will be listening, because there will be nothing left aboard to speak. If the Oort cloud is held so loosely, a reasonable thing to ask is what happens when something passes through it. That is not a hypothetical. It happened recently enough that there were people alive to see the sky it happened under. About 70,000 years ago, a small binary system, a red dwarf of roughly 9% the sun's mass, paired with a brown dwarf, passed within about 52,000 astronomical units of the sun. 52,000. That is inside the Oort cloud by most estimates of where the cloud sits. A star came into our solar system, moved through its outermost region, and left. The object is known as Schultz's star, after the astronomer who cataloged it, and it is currently about 20 light years away, moving off. Its close passage was reconstructed in 2015 from its distance, its motion across the sky, and its velocity toward or away from us. Three numbers that run backward put it inside our outer cloud during the late Pleistocene. A 2018 study went further and looked for the fingerprints. The researchers examined roughly 340 objects on hyperbolic orbits, paths that are not closed loops, and found a statistically significant clustering in the direction those objects appear to come from, in the constellation Gemini, which is where Schultz's star would have been. The interpretation is that the flyby disturbed a population of distant bodies and sent some of them onto new trajectories, a few of which are still arriving. That interpretation is a finding, not a settled fact, and it should be held as one. The flyby itself is on much firmer ground. Here's the part that stays with you. 70,000 years ago, modern humans were spreading out of Africa. There were people on this planet with our brains and our hands, and above them, from time to time, a faint red point of light that was inside their solar system. Nobody noticed because there was nothing to notice. A dim star among other dim stars, at a distance where the difference between inside and outside cannot be perceived at all. The most dramatic thing to happen to the outer solar system in the human era passed entirely without witness, and we only learned about it in the last decade. We come now to the last boundary, and it is the only one that answers the question in the terms most people actually mean when they ask it. Forget wind, forget ice. Ask instead how far out the sun still rules. Out to what distance an object, left alone and undisturbed, would continue to orbit this star rather than wander off into the galaxy. That region has a name, the Hill sphere, or the sphere of gravitational influence, and its logic is straightforward. The sun pulls on distant objects, so does the combined mass of the Milky Way. Close in, the sun wins by an overwhelming margin. Far out, the galaxy wins. Somewhere between the two, there is a surface where the influences balance, and inside that surface, an object stays. Outside it, the object is gone. Estimates place that surface somewhere between 100,000 and 200,000 astronomical units from the sun, roughly 1.5 to 3 light years. Every part of that sentence needs its hedge. There is no measured boundary out there. Nothing has ever been observed at that distance in that region, orbiting our star. The figure comes from calculation. The sun's mass, the galaxy's mass distribution, the sun's position and motion within it, and calculations of that kind carry real uncertainty. What can be said confidently is the order of magnitude. The sun's gravitational domain extends a light year or two, and the outer Oort cloud sits near its outer part, which produces the tidiest summary of the night. The outermost ice we believe belongs to the sun sits at roughly the distance where the sun's gravity is about to stop mattering. Those two facts are not a coincidence. The cloud extends as far as it does because that is as far as the sun can hold anything, and it stops there because past that point, over billions of years, everything that was there has already been taken. The edge of the solar system, on the definition that means the most, is the place where the galaxy started winning. The taking has a mechanism, and it is worth describing because it is the closest thing this episode has to an actual physical edge. The Milky Way is not a point mass. It is a vast disk of stars and gas, and the sun is inside it, orbiting the center. That means the galaxy's gravity does not pull on the solar system uniformly. It pulls slightly harder on the near side and slightly less on the far side, and slightly differently above and below the plane. That differential is called the galactic tide, and it is the same kind of effect as the moon's tide on Earth's oceans, operating across light years instead of miles. Close to the sun, the tide is irrelevant. The sun's grip is far too strong for it to matter. Out at tens of thousands of astronomical units, where an object is bound by the thinnest possible margin, the tide is decisive. It stretches orbits. It lifts the outer members of the cloud away over millions of years, and it drops others inward, which is one of the main sources of the long-period comets we see. Passing stars do the rest. Schultz's star was one event. Over 4.5 billion years there have been many, and each one takes a share. So the outer boundary is not a static line. It is an ongoing process, an erosion. The Oort cloud is not simply sitting out there. It is being slowly stripped, has been since the beginning, and the objects remaining tonight are the ones that have survived 4.5 billion years of the galaxy pulling at them. The solar system does not end at a wall. It ends where it is being worn away, and the wearing has been going on the whole time. There is a consequence worth drawing out. The Oort cloud we are describing tonight is not the one the early solar system had. Models suggest the original population was substantially larger and that a considerable fraction has already been lost, stripped away star by star, tide by tide, across 4.5 billion years of orbiting the galactic center, which means the outer boundary has been moving inward the entire time. Whatever number we settle on tonight is a snapshot of a shrinking thing. The sun holds less than it used to, and will hold less again, and the region we are calling the solar system is smaller now than it was when the Earth formed. Nothing about that process is dramatic at any moment you could point to. It is one object every few thousand years, quietly ceasing to belong. If the sun has been losing material to the galaxy for billions of years, it follows that every other star has been doing the same, and that the space between stars should contain a population of objects that belong to nobody. We have now seen 3 of them pass through. The first was detected in October of 2017, moving too fast on too open a path to have come from anywhere in our system. It was named Oumuamua, and it was small, elongated, and gone within weeks. The second, 2I Borisov, arrived in 2019 and behaved like an ordinary comet in every respect except its origin. The third and most extreme was found on the 1st of July 2025 and designated 3I Atlas. Its orbit has an eccentricity of 6.145, a number far beyond anything a bound object can have, and far beyond the first 2 visitors. It came in at roughly 58 kilometers per second relative to the sun, rounded its closest approach at about 1 1/3 astronomical units in late October of 2025 and is now on its way back out, never to return. 3 objects in 8 years, after none in all of prior history, which tells you the detections were limited by our instruments rather than by the traffic. The surveys got better, and the visitors turned out to be there all along. This is the last thing to understand about the boundary. It is not only fuzzy and disputed and enormous, it is permeable, continuously, in both directions. Material the sun has lost is out there in the galaxy. Material other stars have lost passes through here at a rate of roughly 1 detection every few years. The solar system is not a sealed container that things occasionally leave. It is an open region with a slow current running through it. And each of those 3 visitors, on its way in, crossed every boundary described tonight in reverse order. Each one passed through the sun's gravitational domain, then the outer Oort cloud, then the inner, then the long corridor, then the heliopause, then the belt, and arrived among the planets where our telescopes could finally see it, having taken, on the way in, a journey no object we have built will complete outward in 30,000 years. They were never captured. Their speeds were too high, and the sun's grip at those distances too weak. Each came in, rounded the sun, and left on the far side, and each will be in interstellar space again for as long as it exists. We have never sent anything out of the solar system. 3 things have come through it. One measurement remains, and it is the one that puts everything else in proportion. Proxima Centauri, the nearest star to the sun, lies 4 1/4 light years away. The outer edge of the Oort cloud, at the high estimate, sits about 1 6/10 light years out. The sun's gravitational domain may reach farther still, to 2 or even 3. Which means that between our star and the next one, there is not a great emptiness with 2 points of light at either end. There is our cloud, extending 1/4 to halfway across, and then presumably theirs, extending back toward us. Whether the 2 clouds touch is genuinely unknown, and it needs to be said carefully. We have not detected our own Oort cloud directly, let alone anyone else's. Whether Proxima has a comparable reservoir, how far it reaches, whether the outermost bodies of the 2 systems intermingle in the space between. These are open questions that current instruments cannot settle. Some models suggest overlap. The honest position is that we do not know. But the scale is not in doubt, and the scale is the point. The sun's domain is not a small island in a wide ocean. It is one holding among many, extending out to where the next holding begins, with the boundary somewhere in the middle and marked by nothing at all. And now the pair of numbers we started with can be set in its final frame. Sunlight crosses the mapped, visited, photographed solar system in about 17 hours. It needs 1.5 years to clear the outermost region the sun still holds, and it needs 4 1/4 years to reach the nearest other star. 17 hours, 1.5 years, 4 1/4 years. Those 3 numbers in that order are the whole geography of our situation. And the gap between the first 2 is far larger than the gap between the second 2. That last observation deserves to be stated directly. because it inverts the picture most people carry. The hard part of reaching another star is not the interstellar crossing. It is getting out of our own system first. From the heliopause, where Voyager is now, the remaining distance to the outer edge of the Sun's own domain is roughly 1,000 times what has already been covered. And only after all of that does the journey to Proxima properly begin. And that final leg is less than 3 times longer again. Most of the way to the nearest star is spent leaving home. Here's the thing nobody likes to say plainly, and it is the honest answer to the question this episode was built on. The solar system does not end, it fades. Every boundary we have walked out to tonight is a threshold in a gradient, chosen by people for good reasons, none of them intrinsic to the thing itself. The planets thin into a belt. The belt thins into a scattered disk. The wind slows, stalls, and loses to the gas between the stars. The ice thins across 100,000 astronomical units. The sun's grip weakens until the galaxy's is stronger, and even that transition takes place over an enormous distance and has been eroding for 4.5 billion years. At no point along that entire outward journey does anything stop. At no point is there a surface, a wall, a line, or a moment. There is only a star whose influence diminishes with distance, exactly as physics says it should, until it becomes indistinguishable from the influence of everything else. The word edge is the problem. We brought it out here from a world made of surfaces, coastlines, walls, skin, the rims of cups, and we expected to find its equivalent. What we found instead was a slope with no bottom step. So the argument about where the solar system ends is not really an argument about the solar system. It is an argument about which of several honest boundaries deserves the name. And the answer depends entirely on what you want the name to do. This is not a disappointing conclusion, though it can feel like one at first. It is the same conclusion the science keeps arriving at whenever we look closely at a category we inherited. Pluto was not diminished by the vote in 2006. It was the same world afterward, and we understood it better. The solar system is not diminished by having 4 boundaries instead of 1. It is simply larger and stranger than the version with a border, and the version with a border was never anything more than a convenience. What is actually out there is a star, an enormous volume of nearly empty space, a great deal of ice, and a diminishing pull that reaches for a light year or two before it gives way. That is the whole object. There is nothing at the end of it, because there is no end of it, only less and less of it for a very long way. Take a moment to look back along the way we came. We have crossed the planets, out to Neptune at 30 astronomical units, and found that the poster on the wall was drawn to a scale that could not survive contact with the real distances. We have crossed the Kuiper Belt, 30 to 50, a donut rather than a ring, hundreds of thousands of worlds massing less than 1/10 of the Earth, so sparse that a spacecraft flying through it spent years hunting a single second target. We have crossed the scattered disk out to nearly 1,000, where the objects are on the tracks of things that were thrown. We have crossed the termination shock at 94 astronomical units for one spacecraft and 84 for the other, and learned that the same boundary sits in different places depending on the year and the direction. We have crossed the heliopause at 121 in August of 2012. The crossing the world was told was the edge, and found it to be the outer surface of a bubble of wind, with the sun's gravity continuing on unaffected for 1,000 times farther. We have crossed the long corridor, 2,000 astronomical units of nothing at all. We have crossed the Oort Cloud, a spherical shell of hundreds of billions of icy bodies that no one has ever photographed, reaching a quarter to halfway to the next star. And we have reached the place where the galaxy begins to pull harder than the sun, 1 to 3 light years out, which is as close to an edge as this system has. We have also crossed something less tangible along the way, which is the assumption we started with. The night began with a boundary that everyone knew about and a spacecraft that had supposedly passed it. It ends with 4 boundaries, none of them where the announcement placed it, and a spacecraft 1,000th of the way out. Nothing about the solar system changed tonight. What changed is the size of the thing the word refers to. It was always this large. We were simply working from the poster. So the question can now be answered properly, which means answering it 4 times. If the solar system means the sun and its planets, it ends at about 50 astronomical units, past the Kuiper Belt, and everything beyond is a suburb of debris. If it means the region the sun's wind fills and shields, it ends at the heliopause, at roughly 120, and a spacecraft built in the 1970s has been outside it since 2012. If it means everything gravitationally bound to the sun, it ends past the Oort Cloud, at somewhere around 100,000 astronomical units, and no human-built object will arrive there for 30,000 years. And if it means the full reach of the sun's authority, the last distance at which this star, rather than the galaxy, decides what an object does, it ends at perhaps 200,000, 2 or 3 light years, better than halfway to Proxima Centauri. 50, 120, 100,000, 200,000. All 4 are correct. All 4 are used by working scientists. The largest is 4,000 times the smallest, and the choice among them is not a discovery waiting to be made. It is a decision about meaning, made by people in language. The best claim, for what it is worth, belongs to the last one. Gravity is what makes the solar system a system in the first place. It is what holds the planets in their orbits and the comets on their long returns. It is the thing that was doing the work before there was a wind to measure or a belt to catalog. If any single boundary deserves the name, it is the one where that grip finally gives out. Which means Voyager, after nearly half a century and nearly 16 billion miles, has traveled about 1,000th of the way to the edge of the solar system. It is worth holding both halves of that sentence at once. Half a century is most of a working life, and 16 billion miles is a distance no other object built by anyone has ever reached. The achievement is genuine, and it is not diminished by anything said tonight. And it is 1 part in 1,000 of the way out. Both things are true. That is the actual scale of where we live, and it is the reason the announcement in 2012 was not so much wrong as premature by roughly 30,000 years. Look out a window tonight, if there is one near you, and consider that you have spent your entire life inside a structure whose outer boundary is a matter of ongoing scholarly disagreement. It is not an unfamiliar situation. Almost nothing that matters has an edge you can put a hand on. A city does not end at its limit sign. It thins into suburbs, then into towns that commute in, then into countryside that reads the same newspaper. A language does not end at a border. A life does not end at any single moment that a physician can mark, and the influence of a person does not end there at all. We draw the lines anyway because we need to. A boundary is a tool for thinking, and a tool does not have to be true to be useful. The astronomers who put the heliopause at 121 astronomical units were not making an error. They were choosing something measurable and standing by it, which is what anyone does when the honest answer is a gradient and the work still has to get done. So here's where the night leaves us. In August of 2012, a spacecraft crossed a boundary about 121 times farther from the sun than the Earth is, and the world was told it had left the solar system. Sunlight reaches that boundary in about 17 hours. Sunlight needs as much as a year and a half to clear the outermost edge of what the sun still holds. The gap between those two numbers is the part nobody mentioned. It is where nearly all of the solar system actually is. It is dark, it is enormous, and it is ours. Everyone who has ever lived has lived inside the first 17 hours of it. Every map, every mission, every photograph ever taken of anything was made in that first day of light. The rest, the overwhelming, silent, unphotographed remainder, has been there the entire time, in every direction, holding its ice in orbits that take millions of years to close. You have been inside it your whole life. So has everything you have ever seen. Above you, in every direction, a shell of ice 1,000 times wider than everything anyone has ever mapped. No wall, no line, no last stair, only a star holding on for as far as it can. Good night.